All right, so when we do E2 reactions, we can find the rate equation pretty easily, right? What's the rate equation going to be? It's going to be rate equals K, and is it just times the substrate concentration? And the base, right? So we'd say K times the substrate. And the substrate, it's important to remember, has to be in a reactive conformation, meaning the beta proton needs to be anticoplanar, times the concentration of the base in solution. All right, there's an interesting trend, though, that you'll often see with these E2 reactions. So let's take a look at two cases. We'll take case number 1. And in case number 1, we've got a leaving group with an anticoplanar beta proton. And we also have 2 other protons coming off of each of these positions. And if we have a strong base, for example, maybe it's a hydride base H-, this hydride base can grab this proton, clamp down, and kick off your leaving group all in one step, right? So if we look at the final product for this reaction, we can make an alkene. All right, and then case number 2, I'm going to draw separately down here. And case number 2 is going to be very similar. We're going to have an anticoplanar beta proton, but this time we're going to have a methyl group. Coming off instead of protons in those positions. And just like before, we can treat this with a hydride base. Oops, this should be a CH3 over here, excuse me. In fact, let me draw out the protons for that, and you'll see why in a second. You can clamp down, kick off your leaving group, and you'll get a tetra-substituted alkene, plus you could have a minor product where your base clamps down, grabs that beta proton, kicks off bromine there. Which one's going to be major, the left one or the right one? I would say the left one, right? Hydride's a small base, so this would be your major product. I'll just put this one in parentheses and say minor product. So we would get a combo of 2 different products for this bottom one. All right, so now let's kind of zoom it out and look at each of these. Which reaction do you think is going to be faster, the top one or the bottom one, and why? Let's think about the transition state, right? So the transition state for the top one, if we think about it, the bromine is falling off that central carbon. You're forming a new pi bond between those 2 carbons. You're losing the proton down here, and it's covalently bound to your hydride that's incoming, right? So let me fill in the rest. Got a hydride, hydrogen there, hydrogen there. The bromine, when it falls off, has a partial negative. Whoops. And then the hydride, as it comes in, is partial negative. Does it look like this double bond is being very stabilized? No, it has no hyperconjugation stabilizing the formation of that pi bond, right? So it's relatively unstable. Let's take a look at the bottom example. Okay, and I'm going to focus on the major product. That's the one we're really thinking about most right here. So just like before, our bromine's going to fall off that central carbon. Our pi bond's going to form. Our anticoplanar beta proton's falling off. And our hydride's forming a new covalent bond. We have these methyl groups coming off here, 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 and here. Just like before, whoops, this bromine is going from neutral to negative, so we'd label that as partial negative. and the hydride went from full negative to neutral. So we've got two different transition states. This transition state on the bottom is a lot more stable due to the hyperconjugation imparted by each of those methyl groups. So this should be the more stable transition state. Due to hyperconjugation. All right, so now going back to our original question, if you have a more stable transition state, does that make the rate faster or slower? Faster, exactly. So this would be the faster reaction because it has a lower activation energy, meaning it takes less energy for this reaction to occur. So ultimately what this means is that when you're comparing two different E2 reactions, the E2 reaction that gives you the more substituted alkene will generally occur at a much faster rate than the E2 reaction that gives you a less substituted alkene. So let's make a note of that. So E2 reactions that give more substituted alkenes occur at a faster rate because they go through a transition state that is more stable. Does that make sense? Yeah.
So what about when we have a Hoffman product? Because we know they go out to the lower substitute.
Yeah, so Hoffman elimination reactions typically occur at a slower rate.
Well, I just mean if there's like two Hoffman reactions,
So if they're
substituted Hoffman versus a one substituted Hoffman.
That's a good point. So you're asking about potentially different Hoffman elimination products. Yeah. A Hoffman product, by definition, is your least substituted product. But when you have a really big, bulky base, oftentimes it's your major product due to sterics. This is a little bit weird here, right? If we're looking at case 2, we invoked an argument about electronics, right? We said electronically the transition state is more stable due to hyperconjugation. We weren't really looking at sterics in this example. How many of you had a chance to watch that supplemental video that I gave? Yeah, I kind of went into the nitty-gritty detail about activation energy and Gibbs free energy and all that stuff. I would really encourage you to watch that if you are struggling to understand what does it mean when I'm talking about more stable transition state or more stable product, because it is kind of confusing for E2 chemistry. Does this make sense so far about reaction rate? All right, so let's really quickly wrap up E2 chemistry. And the big summary takeaway is if you have a strong small base, you're going to favor your Zaitsev product. And if you've got a big bulky base, you're going to favor your Hoffman product. That doesn't mean you exclusively get one product over the other. It just means you're changing the relative ratios in solution, right? In addition to this, we said that the rate for an E2 reaction is second order, where you have your base concentration times your substrate. And like we just said, the substrate has to be in the correct conformation in order for E2 chemistry to occur. All right? The other thing that we said is the rate is faster for formation of more substituted alkenes. All right, so what we're going to do for the remainder of the week is we're going to be looking at the competition between SN1, SN2, E1, and E2. Tomorrow when we come in, we're going to look a lot more at E1 chemistry. I think we have a little bit more time. There was one last point that I really quickly wanted to get into. This is more just a vocabulary thing. Oops. So let me change to my reaction mechanisms here. All right, so vocabulary that you might see when you're looking at E2 reactions. The first term is pretty easy to remember. It's stereospecific. And when you hear of a reaction that is stereospecific, what do you think that means? It's going to give you one specific stereoisomer, right? So it's a reaction that gives one stereoisomer as a product. So you may see this term floated around on sapling or in your textbook. It's pretty easy to remember though, because stereoisomer specific means you only get one, right? Where it gets tricky is this next one. Stereoselective reaction. So the way I remember this is if you're specific, that means you're going to the grocery store to buy one specific thing, right? So I might go to the grocery store and want to buy Pop-Tarts, right? If I'm selective, that means I want breakfast food, right? It's a kind of different rationale here. What do you think that means? We could get a broader range of products. So it's a reaction that gives an unequal mixture of stereoisomers. So, for example, maybe we're getting a mixture of enantiomers. Maybe we're getting a mixture of diastereomers out in an unequal ratio. That would be a stereoselective reaction. You prefer one over the other, but you ultimately get a mixture of the two, right? All right, and then the last vocabulary term is regioselective. All right, a regioselective reaction is a bit different. It's a reaction that gives an unequal mix of constitutional isomers. So just like before, we said we're getting an unequal mix. But when we're talking about stereoselective, we're talking about stereoisomers. When we're talking about regioselective, we're talking about constitutional isomers. So when we're looking at Hoffman and Zaitsev products, which of these three do you think it would be? So when we have a Hoffman product versus a Zaitsev product, are they the same connectivity? No, the double bonds are in different positions. So which one would it be then? Regioselective. So oftentimes when you're reading through your textbook, it will refer to these E2 type reactions as being regioselective. And that's because we're getting two different constitutional isomers in an unequal ratio. Does anybody have an example of a stereospecific reaction that we've learned? Substitution, which one? SN1 or SN2? Which one only gave one product? SN2, right? When we did SN2 reactions, we exclusively got the inverted product, so we could call that stereospecific. If we think about stereoselective, SN1, we said we had a slight preference for inversion, so we generally get a little bit more of that than the retention. So we could argue SN1's more of a stereoselective reaction. There are also E2 reactions that are stereoselective as well, where you get an unequal mixture of diastereomers. So maybe you get trans favored over cis slightly. So there are examples of E2 chemistry that fall in that category as well. Yeah?
Are there E2 reactions that are stereospecific?
Yes, absolutely. There are some E2 reactions that are stereospecific. If we think about an example of that sort of reaction, it would be a reaction where we only have one beta proton, so we only have one possible product that could form, and we could argue that reaction is stereospecific. So it is getting into a lot of semantics, but I like to clarify vocabulary just in case we run into it. So try to make sure that you remember these three key ones. All right, I think that's going to be it. Tomorrow we'll come in and talk about E1 chemistry.